Hello. This lecture will cover pages 66 through 68 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Operational Amplifiers, Chapter 4C, the Unity Gain Amplifier. We're going to start out looking at page number 66, Practical Op-Amp Circuits. We're going to discuss three op-amp configurations. The Unity Gain Amplifier, sometimes referred to as the buffer amplifier. We're going to discuss a inverting amplifier and a non-inverting amplifier. This lecture we discuss just the Unity Gain Amplifier. We're going to have two more lectures. One will discuss this and one will discuss that. The first step in analyzing operational amplifier circuits is you have to determine whether it's a Unity Gain amplifier, whether it's an inverting amplifier, or whether it's in the configuration of a non-inverting amplifier. That's going to be your first step. But to start out, let's look at a Unity Gain amplifier buffer configuration. I want you to notice that it takes the output and it brings it directly back to the inverting input. That's negative feedback. It doesn't take a portion of the output. It takes the entire output voltage and it brings it back with negative feedback. Anytime you see the output brought back directly to the input and it's an inverting input, that is a Unity Gain amplifier configuration. Notice that the source voltage or input voltage feeds into the plus terminal, the non-inverting terminal of the operational amplifier. Let's use the model and find the voltage gain for this closed loop configuration. The operational amplifier still has in its specification an open loop gain, which is infinity. But when you put this feedback path in, the ratio you get of V out over Vs is a closed loop voltage gain. The voltage gain here is going to be a closed loop voltage gain because it's a closed loop system. And it's defined as V out over Vs. So what we're going to do here, if you take a look at the next page, which is on page 67, we're basically going to take this model, which we had on page 65. And what do we have to do to this model to make it a Unity Gain amplifier? We simply take this output here and we draw it back to the negative input. So you're going to see a line, a wire that makes a connection from here to here. That's all. And that's what you're looking at here. I referred to this voltage here as Vn, which is the difference between Vs, V plus minus V minus. That's Vn. Here's our Ri, our input resistance, and here's our R out, our output resistance, and here's our current or voltage controlled current source, our dependent source. We're going to form two loops here. I'm going to form loop number one. I'm going to call it current I. This analysis we've done before. Didn't look like this circuit, but you should be able to do this analysis. I'm going to start here. Here's my loop one. It goes up this way, comes down, comes over, and comes down to here. Let's do that again. Here's just loop one. And I'm back to here. I showed it with this line. Around loop 1 by Kirchhoff's voltage law, a plus Vs minus Ri. Then you stop and think. What current goes through it? I. Just as one current, I. Minus R0. Stop and think. What current? I. Then you have a minus A0 Vn. Well, we know what Vn is equal to. We're just going to make the substitution in a minute down here. But we clean this up. We know Vn is... What's Vn going to be? Well, it's the current times Ri. The current I times Ri. I make that substitution here. There's my first system equation. Vs is equal to I times this quantity. A very easy algebra, but pretty powerful technique, analysis technique that you should see by now. That's what this class is all about. Around output loop by Kirchhoff's voltage law. I did another loop here and I started at this point and I went around this little loop right here. I did it a counterclockwise direction just to show you can go in any direction. I did it a clockwise, got the same result. I did a counterclockwise direction. This is an open circuit though. There's no current there. I'm just going to do Kirchhoff's voltage law around that loop. There's no current. So around loop 2, counterclockwise, starting down here, plus V0. You should be able to see that plus V0 right there. Plus V0. Minus R0. Then you stop and think. What current? I. Just our loop analysis. That's the only current that goes through there is I. Okay? And then you look, you have a minus V out, V in right here. Then you're back to this point again. That's it. Clean that up. You get what V out is. You form the ratio. That's what this is all about. The closed loop gain of this circuit, when we use this model, is simply equal to this. Well, the I's cancel, and since R out is much, much less than R in, Ri, I mean, this was what, 200 ohms we said? Typically, this is 100,000 ohms. So this swamps that out. So you can see, you can basically forget about it up here. The Ri's cancel, and you get the gains approximately equal to 1. That gain is approximately equal to 1. When you have this configuration and you see it, if you have 10 volts here, you get 10 volts out. If you have 2 volts here, you get 2 volts out. If you have a minus 5 volts here, you get a minus 5 volts out. You might say, well, what good is that? Well, you're going to see in an application in a minute what that does for you. And your second lab, we're going to talk about that. But this gain is only true when you recognize you have a unity gain amplifier. And if you go back and look at equation A, remember the control theory equation I gave you where the closed loop gain of a system is the open loop forward path gain, G, divided by 1 plus, if it's a negative feedback, 1 plus the loop gain, G, which is the open loop gain, times H. You plug that all in here, you get 1. Some engineers don't go through this anymore. They don't go through this analysis. They just use this. Well, how am I getting H being 1? Well, look. You know what this is up here. This G up here is the open loop gain. This is the closed loop path. So what's the open loop gain? It's A0. It's infinity. This is all going to cancel out here in a minute. It'll cancel out. But how do you get H here? This is H. Well, if you have V out here and you have V out here because it's just a wire, what's the ratio of V out over V out? It's 1. So you can put a box here and put the block diagram for that. It's just going to have a box there with a 1 in it because you're feeding 100% of it back. I put the 1 in right there. What's 1 plus infinity? It's infinity. Infinity over infinity is 1. This is a real quick analysis over here. But you're going to see that in future classes. I like to introduce it now. Show you. But unity gain. Look at page number 78. On page 78, we have an application here of the Unity Gain Operational Amplifier. Here I have a simple circuit. VS driving a Unity Gain Amplifier because it's taking the output back to the negative input. And I have a load resistor of 1K. Remember, in this circuit here, Ri is approximately equal to infinity ohms and R out is approximately equal to 0 ohms. So what is VL? What's that load right there across the load resistance? We called it V out, but V out and VL. V out is exactly equal to VL in this problem here. What is VL for VS being 10 volts without the amplifier in the circuit? We take this amplifier out. We just make a connection between there and there. Just draw it in. And tell me what VL would be. Go ahead and work that out. And then put this amplifier in the circuit and tell me what VL would be with exactly the way it's shown here. Stop the video and work that out, and then I'll show you my solution and you'll see what the benefit of this is. If you did that and you worked the problem out, this is what you'd find. Without the operational amplifier in the circuit as a unity gain buffer, the load voltage is 5 volts. The efficiency is 50%. You give 10 volts over here, you're going to end up with 5 volts. Now you could calculate the current and take it times RL, but it's just the voltage divider rule. 10 times 1K divided by 2K gives you that voltage at that point with respect to ground here. It's 5 volts. You only get 50% efficiency. from that. Down here, if you put that in the circuit, it does a number of things for you. A lot of engineers will use that. First of all, if something happens out here, or something, this is another circuit that's modeled as a 1K resistor. If this circuit gets damaged for some reason, it might take out this device, but it protects whatever's back here. That's why it's called a buffer. This could be a circuit. This could be another part of a circuit. You put a buffer in between. Something happens over here, it takes out this and leaves this intact. So it protects this circuit back here. But what else does it do? Well, if you take a look, and this is the way I want you to analyze this. Notice that the input resistance here of the ideal operational amplifier, I said you could treat it as infinity, and we have, and we will in future analytics that we go through. If that's infinity, that 1K resistance does nothing. 1K plus infinity. There's no current flowing there. There's actually no load from this. Now that 1K ohm resistor, you're going to find out, is really part of that source. See, no source is ideal. No source is going to put out, ideally, 10 volts. As current starts to go, there's a voltage drop inside an internal resistance that's in here. We're just going to start pulling that out, and we're going to show in that resistance up here. We're going to call it the source resistance. So anytime you see a resistor up here, it's just going to be the source resistance pulled out of this practical source. So we can make this an ideal 10 volts, but when current starts going, the terminal voltage here will be somewhat less because you have a voltage drop there. Not in this case. Why? Well, first of all, use the voltage divider rule. If that's infinity there, 10 times infinity divided by infinity plus 1K, you get all 10 volts right there. But another way of looking at it is there's no current flowing. If you don't have any current flowing, you can't get a voltage drop. So 10 volts there puts 10 volts there. Stop the video, back it up for 1 minute, and listen to what I just said. You have to understand that. So now we have 10 volts at this point. It's a Unity Gain Amplifier. It puts 10 volts out there. 100% efficient. Voltage across the load is 10 times the gain. The gain is 1. You get all 10 volts out here. Every bit of that 10 volts gets delivered to that load. 100% efficient. Why does it do that? I explained it to you as I went here, but here it is again. That operational amplifier has an infinite input resistance here. So that 10 volts basically there's no current that flows here, so there can't be a voltage drop. So if you have 10 volts there, you're going to have 10 volts there. If you want to look at it in terms of no current flowing, if you want to look at it in terms of the voltage divider rule, 10 times infinity divided by infinity plus 1K, it's 10 volts. And that being a Unity Gain Amplifier, because we have this connection tied to this connection, the output that's generated, that output resistance is very low, which is a really good thing because the voltage that's generated inside here all gets put out here because of the same reason back here, except the reason is that resistance is very, very low. So you have 10 volts here, we'll say, times 1K divided by 1K plus 0. You get 10 volts there. Output resistances being real low on devices is a real good thing, just like input resistances being real high is a real good thing. That's an attribute having infinity coming in for the reasons I explained, and that's an attribute having that as a very low output resistance to get all of the voltage or majority of the voltage that's developed inside this active device across that load resistor. That's the reason this particular amplifier the Unity Gain or buffer amplifier configuration is very, very important. That's the Unity Gain Amplifier. We have 2 more amplifiers configurations to talk about. The next lecture will cover the inverting amplifier and then finally the non-inverting amplifier. That concludes this lecture.